electrons battle to find the stinkiest substance.
Yeah, that's always a good one. All right. Happy Thursday. All right, so make sure if you're in person, I printed out kind of the cheat sheet. But again, if you're online, right, this is essentially kind of the answers. And as you go through your homework, right, obviously you're just going to have deviations on the total electron count. So that's really all that we're doing is once we get our skeletal structure of, again, yes, SP mixing for these elements and going in this order. And we observed, again, that our pi bonding is lower, right, than our PZ. Again, with mixing, and then without mixing, our Z, right, PZ is lower in energy from that head-to-head favorable interaction there. And then our pi through space interaction. So again, that's no mixing. And like I mentioned, if we have elements that are kind of mixing like CO or something, then I'm going to explicitly tell you either mix it or don't mix it, that sort of thing. You could also do a comparison, right? Do a diagram of it mixed, do it unmixed, which one is kind of true. And so that's kind of the point of this exercise. And like, you guys are like really amazing, asking so many questions, like really trying to deeply understand this. And like, what I want you guys to understand though, is we're trying to like quantify this quantum mechanics like simply, right? So, and we're trying to give the properties of these atoms and like trying to figure out, well, how can we simplify them with this line structure? You know, what else do we need? Because what we're trying to do is figure out how to describe them, right? And describe the reactivity. And so kind of where I'm going with this too is, right, we understand kind of why we need to take it to a deeper level because of the observations that we see. And then that being said too, like things are not maybe as simple as we think they are. And so again, like that's where the computational chemistry is kind of powerful to maybe try to compute those interactions, right? So again, talking about these outer, like the electrons moving around and all their orbitals and what that does. So again, we're like trying to take this very complicated concept of like, how do we describe these electrons that are moving near the speed of light all around these little atoms and how that exists, right? And we're trying to, let's just simplify it to this paper. So yeah, that's what we're doing, and what we find, it is really powerful, but that's, again, kind of where we're at, and we'll kind of see some things. So let's start with oxygen, and so we had teased it. So let's kind of go back to where we had left off. And again, this is a good place to understand where our MO diagram gives us more detailed understanding than, again, our Lewis dot structure. And this is like the other beautiful thing I think about a lot of chemists. And I was kind of talking to Kevin Murphy, not to put him on the spot. I was like, Kevin, I'm still talking about you. But then like part of the reason why we're still talking and why I love chemistry is like so many chemists just have the fundamental love of like knowledge. And so, and that's the other thing you have to understand is like, yes, in my PhD program, I said that I was going to save the world from CO2, and right, we're going to turn CO2 into fuel, and it's going to be no problem. And that's not really, though, what the goal of our research was, though. What we actually cared about and what my boss cared about and what we all cared about in lab was making cool bonds and seeing cool stuff and doing new reactions, new reactivity, right, that has never been done before. And so to me, right, that's just the pursuit of pure knowledge, and that's beautiful. And not to get on my soapbox, I wanted to get on my soapbox today, but it's like that's kind of why we're here, and I want us to kind of remember that too. It's like we're here pursuing knowledge, right? We see something, and then we want to understand why, and that's what chemists are always doing. It's like, what is the exact mechanism? And that's what's really beautiful, especially as you go into like higher level OChem and they do all these fancy label experiments. Like these guys are brilliant, and they're getting the data, right? Like they are tracking or trying to track every step to break down like a mechanism, and it's beautiful work. It's quite fascinating. And really some of the most brilliant people are organic chemists that I've ever met. But again, it's like being able to solve this problem. And so what we're doing here is being able to understand kind of the fundamental tools that we have, kind of what are we looking for, what patterns do we start to see, and right, again, build the tools in our arsenal. And so thinking back to our first week's lab, like that was kind of the point of the lab, is like we're dipping our toes in to computational chemistry, because again, what we do in research, and I'll show this paper later, again, I get way too excited about this topic in general, but just like research and all the powerful things that we're trying to show, but that's the whole point, is does the computational chemistry match what you're observing in lab? And then you do all these experiments to prove that and really try to dial that in. And they're very detailed, specific experiments. But like I said, we'll kind of look at a paper in a second, but let's go back to this. Okay, so we're at the problem that our Lewis dot structure, again, does not show the observation. So let's show the observation. So let's go over what we're doing today. So I want to condense liquid oxygen for you. And we're kind of, I'm not saying cheating, but I mean kind of cheating in the sense that I wanted to just bring a tank in. So we have just a tank of oxygen on the side here. And just a note for safety, So again, these cylinders, if you remember from your lab, gas cylinder under pressure. So that's why I have it bound here with the cart so that it's not going to tip over. And I got some of the the stockroom workers to come help me move this, again, for safety. So, right, that's another safety measure. Always tag team things if you need. In chemistry, there's a lot of heavy tank moving. That one's pretty small, but just saying. All right, so the idea is, so we have liquid nitrogen, and liquid nitrogen is colder than oxygen. And so what we're going to do is I'm going to fill this up with liquid nitrogen. So this is just a little dewar here. And these dewars, again, just so you guys know, they're double-walled, so they're vacuum-insulated glass. So that's what's able to keep in the liquid nitrogen. So that's kind of the hardest part of liquid nitrogen, is like getting a container to work with it. And I'm not sure how much this dewar costs, several $100s. I should know, I've exploded not these, but other ones in my life. But this one costs $900 to, again, keep that liquid nitrogen nice and safe in there. And then other notes, so this is just a loose cap, just to, again, kind of lightly cap this. And this is a common thing too. I'll try to show the video a little. But notice, right, for liquid nitrogen, the cap needs to be able to come off. And if you were to ship a sample, so I think I've mentioned this, that like sometimes you have air-sensitive compounds that you got to ship off for elemental analysis. And if they're really, really sensitive, I never had to personally do this, I just watched other people do this. You can ship your sample in like liquid nitrogen or CO2 or something special. But again, these things have to come off because obviously your nitrogen is always off-gassing. And then let's look at some more fun things before I start opening the valve here. So you can always, this is the beauty of YouTube, so you can always find people doing really dangerous things. But from a safety perspective, what we would say as a chemist is, in general, or at least, again, so my training is inorganic chemistry, so we do a lot of air-free stuff, but the big hazard that we have is anytime that you are pulling a vacuum and you have a liquid nitrogen here, if you have a leak in your system, you have the potential to condense liquid oxygen. Then, obviously, you guys know that oxygen is a wonderful oxidizer. Well, it's even a more wonderful oxidizer when it's in its liquid form. And so I think these guys are like, I can't quite tell. I don't like listening to videos. I read things, but I think they're like Russian or something. But you can always find doing people crazy stuff. So this is what we're going to watch just to kind of warm up. So this is why you would not mix an organic. And so again, that's the danger, is if you ever accidentally condense some liquid oxygen in your trap, and then you're pulling off solvent, because that's generally what you do all day is pump solvent off. That's a joke. But once that solvent warms up, boom, you could have a bomb. So if that ever happens, and that did happen one time, not to me, but I've seen, again, other people do it, you just evacuate the lab, and hopefully the vacuum pump will take care of it, right? And the oxygen will go away before anything explodes. But let's watch this video. Let's see if I can...
Catastrophe it is often made out to be. So we used a pipette and dropped in like 20 milliliters of methanol into the liquid oxygen, which is quite a bit compared to what you would expect in a cold trap.
There we go. Obviously, again, we don't want to have...
The result was a bit underwhelming, to put it mildly. Because of that, we moved on immediately to testing charge.
So yeah, obviously you can find, and then you can get sucked into watching people blow stuff up on the internet there. All right, so let's look at our setup and what we're doing. All right, so let's first pour in our liquid nitrogen. So I'm just gonna, again, fill this dewar up. And then, not to give you guys too many ideas of ways to do explosions at home, but you can watch people on the internet. So if you had liquid nitrogen, and if you like pipette air in, like eventually you should condense oxygen. But like I said, I don't want to do that, so I'm hoping my tank is still good. I'm just waiting for that to cool. I'm gonna add more nitrogen. So I believe liquid nitrogen is at 77 Kelvin, but someone on the computer can verify that. Okay. All right, so now I'm going to start opening up my tank here. So I just you have your valve here just to open it, and then this is just your pressure regulator, but this should be set, but I'll still open it carefully in case it... Come on. There we go. All right, so let's... And so now you guys can finally believe me too. So now we can see in its condensed form, right, that it's blue. Just checking you can see that on the camera. So yes, oxygen is blue, right? People weren't lying to you. And now, let's see, sorry, trying to also make sure that the online people can see this. Woo! And so now what we're going to do is test whether it interacts with this magnet here. So I have this magnet, and so let's see how oxygen behaves. And so do you see it interacting? And if you're in the room, right, feel free to get closer. And we can always do this again, right? So you can come up. Oh, wait a second. Hold on. Whoop. So yeah, I mean, don't worry. It's going to be off-gassing. So again, I'll do it again. And so look how it sticks there. And so again, right, that was the observation that people noticed, that it's attracted to magnets. So it's that behavior that, again, showed, okay, well, something's wrong with my Lewis dot structure, right? I have to figure out how we can account for this. And so, again, that's how we get MO theory, and looking at our notes up there, like, yes, we have our paramagnetic with our unpaired electrons. And let's see. Oh, ran out there. And so other fun things to do, you could always throw a match in there. Obviously, that'd be nice and fiery. I just didn't want to do that in here because we're like a little close, so for safety. But then let's compare it, right? So let's compare it to nitrogen. Sorry, camera. And so if we look at nitrogen, this might be hard to tell, but if I pour it on there, right, it does not stick to the magnet. So I'll try that one more time. So again, right, does not stick to the magnet. And so that is telling us, again, the power of MO theory, right? So that's where we can look at our MO theory and then, okay, well, nitrogen is diamagnetic by our MO theory as well. So this is why, right, this is all a good approximation. And so we'll look at some other stuff in a second as well, because what's also kind of fascinating, and I brought this along to talk about today, which is, have you guys seen this before? You might have seen it if you're in physics, but it's basically how copper induces eddy currents, right? Basically, it has some sort of magnetic attraction. So I'm trying to do it for the camera. And so obviously, we can launch it in a regular tube. So this is just a tube. And it falls, oh, and you're not supposed to drop the magnet. Luckily, this is not a super strong magnet. Yeah, but you don't want those like rare earth ones or super strong ones to drop because they could shatter, and then you have like 1,000 shards everywhere, so safety tip. But now if we do it through the copper, so see how it, yeah. And so it's just showing that interaction. But again, right, why this isn't quite clear. But so before we start kind of looking at what I say is exciting stuff, I know where you guys are truly here, and it's for the marshmallows. It's okay, you guys can admit it. Woo! Okay. That's just oxygen. All right. And so obviously, this is a fun thing to do. So if you're not here in class, you can, if you come to lab today, we'll probably still have marshmallows. But have you guys ever seen like the dragon breath thing on TikTok? I think it is. Yeah, so that's how you do it with liquid nitrogen. And so yeah, marshmallows are good. So I'll freeze some marshmallows. And then if you guys want to eat them, you're more than welcome to. Yeah, so marshmallows work well. They get nice and crispy. Other fun things to do for like small children is you can flash freeze flowers and then they shatter. You can do that with like any organic produce, but flowers make a much easier cleanup than like, I don't know, oranges, bananas. Don't do bananas. Bananas are disgusting for the cleanup. I speak from personal experience. Okay, yeah, you guys can get marshmallows there. We also have large ones, if anyone's brave. Yeah, just come up. Don't be shy. Large ones. Okay. Kind of. I'm surprised you guys aren't rushing. I thought that was all anyone came to chem class for was for marshmallows. Does someone want a big one?
Yeah, give me that big one.
Oh.
I want to do a big one really bad.
Okay. Marshmallow. Some ASMR. marshmallows. Yeah, you can always grab. You guys are so shy about it.
Don't hurt you, just gotta move fast.
Yeah. So yeah, other I don't know if you heard Max's joke, but like it's totally true is you just got to move fast. So yeah, like I don't know if you've seen people in YouTube videos, like you can stick your hand in liquid nitrogen, you just don't want it to pool on you at any point. So that's where it gets dangerous. And again, speaking from personal experience, again, if it pools on you, obviously that's going to cause a burn. So marshmallows. Yeah, go for it. You can. I think the garbage is like outside. Huh. Oh, I forgot about it. You wanted the big one. There we go. All right, so if anyone wants more marshmallows, again, just let me know. All right, so kind of. So this is kind of an aside for a second. And again, this is just to kind of show that this whole business of like what's a magnet and what isn't a magnet isn't always straightforward. And so what I mean by that is, well, right, you have this kind of question. So let's first answer the question. Let's start more simply. Is maybe, so why does copper interact with our magnet? And you could, right, think back to first quarter. What could we think about? What could we calculate or write out? And so answer is, right, electron configuration. So hopefully you guys are looking at that. So that's, right, what you're thinking. Again, right, putting yourself in a research chemist thinking brain now, like, all right, I'm going to solve this. So start with the electron configuration. So what do we find about our electron configuration? And what does that seem to kind of tell us? Just like more simply. Yeah, like just what's the I think you're thinking too, just like what's the electron configuration, and then like how many unpaired or paired electrons do we have? Like, yeah, we're just starting simply, right? But then yeah. Yeah, so, okay, so what's our electron configuration? So we'll give it, well, probably, I think we've determined this is a weird one that's 4s1. 3d10 because of the D thing. But to your point, okay, that still means that it has one unpaired electron. So, right, again, that's kind of saying, well, that's paramagnetic then. But then, right, how does this relate to true magnetism, though? And so that's what's kind of like unclear even with research, right? So now let's think about what compounds are magnetic. And so the question is, well, let's compare iron versus manganese, right? And so if you don't know, iron, right, is magnetic or can be magnetized, but manganese cannot. And this is odd. So just write out the electron configuration for a second. And so what do you find for these two? And so I would maybe draw out your kind of d orbitals and sketch this. So what's the electron configuration? Let's start with manganese. So 4s2, 3d5. And so this is the point that I'm trying to make. Okay, if we look at this 3d5 here and sketch what we think it's going on, is right, we predict, okay, well, we have 5 unpaired electrons. But then we find that, again, manganese, despite it being officially paramagnetic here, is not really a good bulk magnet. Now, there is research being done, though, on like nanomaterials or maybe combining manganese with other materials to try to, so this is due to basically to some like relativistic effects. And again, this is where like computational chemistry comes into play. So that's kind of my point here too, is like we start with our simple kind of MO theories, kind of looking at it, but then, right, we come to this next question of, well, this doesn't really explain that well. And so let's finish our sketch. So iron is just looking at the periodic table. Let me pull it up over here. Just 1 over, right? So now it's going to have a pair. So it's 4s2, 3d6. And so it's a little odd now, just thinking about it, that it has a pair, right? A set of paired electrons, and it has 4 unpaired electrons. And then this, of course, has, like I said, magnetic properties. So it can be made a permanent magnet, and they can be all aligned, while, again, manganese cannot be for other effects. Yeah. Oh, I think Ellen. Yeah, I think that's like actually what it is, comes down to is, yeah, there's like due to some symmetric arguments that for some reason they cannot align. But again, that would probably be like better proven by computational chemistry. But yeah, like that's the piece that computational chemistry tries to kind of answer better. And again, maybe like higher level math, because you can get into other like arguments too of allowed or unallowed transitions and other things. But yeah, that's basically it is what the argument is. But like I said, right, it's not obvious kind of looking at it. So that's where we try to go, looking at MO theory, trying to go deeper, trying to figure out, again, the relativistic effects, which then come into play with computational chemistry. Yeah. Yeah, so it's paramagnetic, but like I said, you can't magnetize it. So you can't, right, make it like a permanent magnet, whereas iron, you can get them all to align, right? And then it stays in alignment. So that's the definition of the magnet, yeah. So that's pretty interesting. And then, again, just trying to keep perspective of what this all means in the grand scheme of at least chemistry. So this is an example of a paper that is backed up by computational chemistry. And so basically you make your new novel compound, but then you have to prove kind of what's going on. And obviously that a lot of research and experiments goes into this. And so this is a technique called EPR, and that just tells you like how many unpaired electrons you have. And right, that's where the simulation comes into play with computational chemistry. Again, you're just trying to compare, right? Does the computational chemistry agree with the experiment? And then you can use the computational chemistry to help figure out, again, what those molecular orbitals look like. And so we'll just skip to kind of the pretty pictures. And so that's the whole point of this paper, is like they did really detailed computational work of simulating everything to show, yes, we really have this simulation down. And it's called like the basis set, basically. I'm trying to find where it is in the paper. Here's a pretty picture. But all that like gobbledygook thing that like you were automatically filling of like STO basis set. So I don't quite know what that means. Like I said, I just kind of use this as a tool from the inorganic chemistry perspective, but that's where the research side of computational chemistry goes, of like blah, blah, blah. So this all means stuff of like what basis sets to what details and like all these things that, like I said, I don't fully understand. And to be honest, that's why we did a collaboration with this professor, because he is a computational chemistry professor. And so even my professor is not well versed in this to that detail. So you collaborate, and again, you make sure everything checks out, and you get some data, and you get your pretty pictures. So that's what chemists care about, is being able to model this, and then it tells you, again, your spin density. And again, you're always kind of looking at that HOMO-LUMO gap. That's what chemists care about, right? Looking at any excitation that you can have between that. And then other things you would look at are like cyclic voltammetry. So just like, does it do oxidation and reduction reactions reversibly or not? It's all sorts of things. And so yeah, so that's a paper and kind of what this is all laying the foundation towards, and like what the whole goal is. Yeah. And like I said, I wanted to at least give some perspective. I know we get kind of buried in the day-to-day of like, let's just get our degree and get out of here type thing, but a lot of great research going on just for the sake of research. All right, so do we feel we could do more practice problems with the MO diagram if you wanted, but I kind of feel, at least for now, we'll kind of hit up some other things. Because like I said, this is your cheat sheet, and then your homework is just about like counting the number of electrons and filling that in properly. And then if you need help, obviously come see me. I'm available Monday, Wednesday, Friday. Just make an appointment so I know I'm in my office and you're not like overlapping with other people. Unless you want to bring a large party, I'm fine with parties as long as you guys are fine with it. But yeah, just meet with me. It takes practice, so that's the other thing that I will emphasize is like, just draw an MO diagram like 10 times and then you'll probably start to feel much better about it. Like, it's really just drawing it and really kind of putting the pictures in your mind and everything. And again, it's difficult. Like, this is incredibly high level stuff. I'm trying to emphasize this. We're trying to like really simplify quantum mechanics to little pictures. So it is intense, yes. All right, so the last kind of bit of lecture is a little bit of recap. Again, just kind of looking at our orbital mixing, because that was formally in this chapter. I know we hit it with our geometry since that fit a lot better. But basically, this is kind of showing a little bit better than my chicken scratch how we get our sp hybridized orbitals. So that's where our s orbital kind of got minimized in the center here, just giving us the overall sp lobe picture that I kind of sketch out. And then I like this drawing. Oh, and we can remind ourselves again, right? There's our sigma bond from that direct interaction, just pointing that out. And then H is just represented by a ball, since it's represented mainly by our 1s, right? That's all it has. And then again, showing our px, py, and again, we can switch the axes, however you want to label them, but noting that we have two unmixed p orbitals, right? So one went into mixing, so pz, just for clarity, then px, py are available. So if this wasn't hydrogen, then it could do potentially, right, some sort of pi bond or something. And so that's the difference that's from here to here. So, right, this is hydrogen. And then if we have an fluorine or something that's obviously f orbital based, that's where I kind of made the comment, it's f orbital. And so it's just going to be the one, again, in the sigma direction. So your direct interaction. And these are going to be occupied, right, by electrons, so non-bonding. And again, a pretty picture, or prettier picture, of our sp2 hybridized orbital, and showing our one unmixed p, well, they called it py. We're not consistent with our axes here, but that's okay. But whatever we want to call this, py from our orientation. So again, that's available for a double bond. Oh, yeah.
If you've got two sp2 hybrids that are like higher level bonding, it's always going to form a pi bond, right? Because they both have the px or py.
Yeah, typically speaking. Yeah, so you're saying you have sp2 and sp2, exactly.
Any higher one as well, because it's still going to have the
Or like sp,
like
yeah.
sp3 or sp3d or 'cause they
Well,
all
well, those have those will interact like a little differently though.
they won't have the px.
They're not really like in the same. Like it kind of depends, like how they're interacting. So it gets a little more complicated too, cause like, well now I'm kind of skipping. Let me see. So something that's common is, right, you can have benzene add-on. And so like benzene, for example, can interact with your DZ squared with metal compounds. So I don't know if that kind of helps. So they're going to interact in like a different way is what I'm saying. Yeah, I mean, they could form bonds, but they may not be like just straightforward pi bonds is kind of what I'm saying is like they'll interact. So this is still kind of like a pi bond, but then they're interacting in like a different like way in a sense. I'm not sure I'm explaining it very well. But let's kind of look, since we're talking about it, I pulled this up of these typical, they're called sandwich compounds. So this one is chromosine with this little, this is called CP, or cyclopentadiene. And so there's several variations. These sandwich compounds are pretty common. So ferrocene is the other super common one. But they just interact, like I said. So now you're kind of imagining, and so this is our benzene. And to kind of explain this, oh, I lost my pen. We have, so we have our sp2 hybridized. What did I do with my molecule kit? I actually brought my molecule kit in, and then I left it either in my office or maybe in lab. But I wanted to show you my little baby kit because it's kind of, it's really good to see the hybridization with. But okay, so we're imagining this is benzene, sp2 hybridized, so planar. But then, right, we have all these py orbitals. But then what's being shown here, and I don't know if it's necessarily clear, is so mathematically what's going on, and this is why I'm kind of like yes and no, is you have to figure out mathematically like your irreducible representations. But the other way to kind of look at it pictorially is, again, okay, these things are all in the same direction, right, our py, and so that means we have this delocalized pi interaction. But then this also means, like I was saying, is we have this diffuse kind of pi lobe to then interact with, like I said, typically a dz squared on the metal. And if you can kind of, right, like imagine, and I'm sure there's a paper with this like drawn, but it would take me time to ever find it. But if you can imagine, and well, now I did the shading wrong formally. So, right, clear donut hole, and then my ends are shaded formally, just so I could plop on. I'll try to be cool about this. And then if you could imagine, right, this plopping on around it like so. And then they're all in the same shade, and so they're all kind of interacting there in a bond that way. And so you can kind of see this. There's all sorts of like tungsten sandwich compound carbonyls, so that, you know, you can start with like an octahedral one and then like distort it and swap it out and all these things. So. So then this one would be like kind of more one big like diffuse all orbital like going together, right? Of like, Yeah, because then it'd be a d and a pi interaction, right? But that's your bonding orbitals there of your, so this is like your metal bond then, right? Your ligand to your metal interaction is how you would be looking at that. All right, and obviously you can tell I have too much fun with this section. And so again, just kind of recapping the last bit here, so a better picture representation of our sp3 hybridized lobes and that shape. And then just re-emphasizing what we were practicing. And so that's just something that you want to be more familiar with, get good at. Like I said, if you're quick with your hybridization now, that'll help you for OCHEM. That's all I'm trying to do is like lay the foundation for OCHEM. And I mean, people tell me that this class does lay a good foundation for OCHEM. Like, not trying to toot my own horn, but I'm saying like that's why I emphasize it so much, is like you need to start thinking in 3D now, or else if you go to OCHEM and you're like trying to put things in 3D for the first time, like it will be incredibly difficult. So yeah, so we're thinking, okay, and again, this is where we want to bust out our models. Maybe while you are taking the quiz, I'll try to find what I did with my little baby kit so you guys can play with it better. And then unfortunately on Amazon, it was out of stock. And I'm like quite particular about that kit. You'll see why. Now I've really gone out on a tangent here. But it's really valuable that you have like the correct tools in OCHEM. As a TA for OCHEM, I can't tell you how stressed out I would get. Just like one day we will look at like the terrible kit. I can't find that one. Maybe it's fallen out of fashion. But it used to be in like every bookstore. But then for every OCHEM exam, the students are just like pop, 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 pop. And it is like the most, I don't know, it's like the most anxiety inducing thing. But this is the one that I recommend, but I don't know why it's currently unavailable and it makes me super sad. But why it's so nice is it has these stereochemistry really clearly defined. And so I know that doesn't show, like I mentioned before, the double bond where you don't have rotation in the double bond. So that is a limitation of this molecule kit. But for OCHEM, I think it's way better, right? You have a stereo center right there already built. And so that's like half of what the molecule kits are, is like people just trying to build their stereo center. And again, as a TA, I'm like watching everybody just like trying to build a stereo center just to like figure out the answer to the problem. I'm sweating. I'm sure they're sweating as they're popping these balls off. So yeah, that's why I like this kit. It's just like ready to go, super easy, will make your life easy. Yeah, I haven't gone on a deep dive. My husband is a professional procurement person by trade, so maybe I should give him some work to do. Like, how do we buy that kit? It's very nice. And so again, these are just pretty pictures of the double bonds. So like you guys are observing, and this is really good that you guys are starting to see this. Okay, sp2 hybridized. Yes, there's my available py, then we'll call it, for our bonding. And again, I'm sorry the book doesn't emphasize the shading in this one. So no picture is perfect, but obviously, right, they'd be the same shade in our kind of picture. We could sketch out, so this is forming here. Again, just being able to recognize geometry with OCHEM, especially. So sp2, sp2, and yes, right, just recognizing there's my pi bond. So again, sigma bond from our sp2 orbitals meeting and having favorable interaction. Or, oh yeah, that was the other term. So your homework uses the term, right, like constructive interference and destructive interference. So I always say like in phase, out of phase, but just make sure you're familiar with that term as well. So yeah, anytime you have, again, constructive interference or in phase. So in phase, constructive interference. Bonding, right? Lots of ways to kind of say, like, yes, they are mixing together. The electron density is in the center, right? That's what we're saying with that. And we're just trying to, again, give some electronic sense, right? Predict some reactivity, explain things. And again, obviously, doing back of the envelope calculations of quantum mechanics, essentially. And so this is just to re-emphasize that we can't rotate easily, right? You can't just spin it around because we have our pi bonds. So if we just rotate it, then obviously, right, we would break that. So this is not an easy process. So, right, I'm not saying it can't happen, but it would either be a high energetic process, or maybe you have to use a catalyst to do that sort of transformation. So it just depends. But typically there's, yeah, some sort of reaction or catalyst that would have to happen to flip this. And triple bonds, so again with our triple bond, like we saw with our hydrogen cyanide here, we have, again, our sigma bond from our sp hybridized, right? So these are sp. Nitrogen is also sp with that lone pair, and then leaving us py, px for pi bonding there. So again, right, that's where our triple bond comes into play there. And so I was looking over the homework for chapter 8, so it looks pretty good. I think most people did a really good job on that. And again, just make sure that you're checking your octet rule, putting in formal charges. So I try to make a few notations, but just double check that all those dots are crossed. And then kind of the end part here, which I kind of talked about, but then we can look at the other parts kind of mathematically, what's going on. But I mean, some people might glaze over, and this may be too much. Other people may be excited, like myself. But basically what's going on is this is going through mathematically how to do the irreducible representations. And the quick way to kind of start seeing this is this first energy level has 0 nodes. So that's where we got that fully symmetric combination. And then this next one, and you can kind of draw this out as 6 orbitals here, so 6, right, molecular orbitals essentially now. So this is our lowest in energy. Again, that's why it usually participates in bonding as well. Then we have our next one. So now this next level has 1 node, and so you can see that that's what they've done. So you can draw 2 mirror planes, which are symmetric. So this one, and right, they use the plus and minus to show shading. So I won't redraw that, but you can kind of see how it's derived. And then this next level has 2 nodes, so 2 planes. And so notice, right, at each node, it changes shading or signs by their convention. And again, same here, so you can draw 2 nodes with the signs as shown. And then obviously our most antibonding orbital, right, highest in energy, has 3 nodes, and so they flip every one, right? So bloop, 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 bloop. And, oh, that being said, right, so it's good to, again, think about these things visually in 3D. Let me see if I can find a good example quickly. But you can also have weird, like what's called side end additions. So, right, I had shown this kind of landing on, like with ferrocene, very evenly. But sometimes you have like side end organic compounds. I can't find a good one. But what I'm trying to describe is like you have some sort of metal, and maybe it's only like half bound to CP or benzene or something. So it's only interacting with like 2 of the orbitals. So that's where that's getting at. But again, you can see where the higher level chemistry right from OChem is going to take it to inorganic chemistry is going to repeat all this sort of pretty pictures, we'll call it. And so again, just trying to put those pretty pictures together. All right, long story short for this chapter though is, right, this is your cheat sheet essentially. But I would still encourage you to understand what all these lines mean so you're not just like drawing chicken scratch lines mindlessly. But yeah, again, it takes time to put everything together. So let it cook with yourself as well. Any other questions or comments or anything? All right, we're probably good to take our quiz then. So yeah, I'll hand out the quiz, and then if anybody wanted to play with anything else, just let me know, obviously. Otherwise, I will see you in lab. And like I said, email me if questions come up. You probably don't want to go to the tutoring center just because I don't think that they would know what the heck is going on in your course very well. And again, that's my reminder, as especially when we get into the equilibrium, the advanced stuff. I've heard stories. They do not know what's going on, and then they like are confused. So just, it's probably much easier if you come to me directly, so you're not spinning your wheels at the tutoring center. It's a problem with chemistry, is trying to find qualified tutors. All right. Let me know if there's any questions. I'm going to stop the stream. Again, you can bombard me for marshmallows or whatever, liquid nitrogen. Yeah. Oh, sorry. I can't count, obviously. Counting is super important. That's why you count your carbons and count them again. That's my #1 rule. Oh, did I short you guys? I didn't make it, sorry. Thank you. Oh, extra? Yeah, I mean, that's how we typically do it, right? Yeah. Oh, no, go for it. Oh, let's